So, good morning, everybody. So, welcome to the event Revolutionizing Medicine and Healthcare, the Power of HPC, AI, and ML for Advanced Medical Solutions. So, my name is Tina Martz, and today I will moderate this event. So, before we start, why this event? So, actually, it will illuminate the transformative role of HPC, of artificial intelligence and other technology in the modern medicine. And today presenters will underscore the crucial synergy between technology, medicine, and eHealth sector, and pretty showcasing the HPC and AI actually plays a crucial role in advancing medical frontiers, optimizing some patient outcomes, and of course, revolutionizing the landscape of eHealth applications. But before we are heading to the presentation, just let me shortly introduce the EuroCC project, which actually supports this event. So the EuroCC 2 project is coming under auspices of EuroHPCGU and partner participating countries, and is running under the Digital Europe program. And its actual aim is to establish the national competence centers within the Europe, which are actually the main contact points in the respective countries for adopting the HPC and relevant technologies for business, for administrative, and for researchers. And just a few more information before we're starting. So please keep your microphones muted all the time to give the presenters, let's say, an easy time. All your questions should be written in the chat, and your questions will be then answered by each presenter by their presentation. And of course, I would like to remind you this event will be recorded. And if you have any kind of other questions, or you would like to get to some information, please do not hesitate to contact me. You can find me in my email in this slide. Our agenda. So we have 5 really interesting and valuable presentations today. So let's start with the first one. The first presentation will be done by Samo Ergen. He's senior research engineer and expert in the field of big data analytics and machine learning at Artur from Slovenia. And he's really actively involved in different R&D projects, contributing to the development of digital tools, applications, implementing AI and ML in different sectors. And today he's presenting the co-founded project CLASICCA, which aims at integrating AI technology into operating theaters for cancer classification, focusing on colorectal cancer. So Samo, floor is yours.
Hello, do you hear me?
Yeah.
And you see my slides also?
Perfectly.
My slide, just to move this one. Okay, already Tina said everything, so I will just go in detail. From my side, I'm coming from Artur. We are a high-tech company, and we are proud to own the largest private-owned HPC in this part of Europe. We are currently engaged in many, more than 30 EU projects, and certainly from this we develop a large network of research and business partners. And as most companies, we also work in many domains, but this project was the first in the medicine, and it became our flagship project. And now we have another one, which will present Jan later in the conference. So CLASICCA is this project EU funded and in area of eHealth or medicine, with duration of 4 years, and in a few months we are reaching the 2nd year of this project. Now, it's very important to emphasize that we are bringing AI in operating room to support clinician in real time during the intervention. We are really lucky to have such important partners in our project. We are 5 university clinical centers, and probably 4 more will join soon. And then 2 law universities, 1 law university from Copenhagen, and Penn State University from the United States, to have the view of law, ethics, and liability from both sides of Atlantic Ocean. And then ERCAT, which is very large training center for clinicians from France. This project was based on numbers or facts, no? That I was really surprised at the beginning, no? That 20% of biopsy diagnoses are wrong. So this is quite there is space for improving this, no? And the other fact is very important, that tumorous tissue has different blood flow, so from the healthy tissue. So when we administer ICG, endocrine green, no? And with the use of near-infrared camera, we capture the fluorescence intensity in time, and so we can look at the difference between the perfusion of through the tissue, no? And again, we do this in real time in the operation room. More on this later. One very important part of our work as we are in the operating room, no? As I'm sure you, with the arrival of autonomous driving with ChatGPT, you are well aware of ethical implications of these technologies, no? And Europe is trying to answer this question with EU AI Act, no? Within our project, we want to create, let's say, legal, ethical framework for AI-assisted in surgical procedures, no? As we are giving the information to the clinician during the intervention. And as you know, no, that law implements ethical and liability views, no? And how it's viewed from the US or Europe is not always the same, and not only in the medical area. US is more oriented versus liability, no? Of those who offering the services, while the Europe is more versus regulation. We can debate what is better. We know that in US everything is going faster, but the liability part is then tricky for the companies offering this kind of solutions, no? And when talking about ethics, it's more complicated. And in this project, we want to cover all the perspective, no? The holistic view approach to ethical questions, no? From law, medicine, and technology, which is what is very, very important, no? Although we decided at the beginning of the project that we should make not a black box, but technically as transparent as possible, this solution for the clinicians, no? Who use this information. Although the black box approach is also promising, but still we want to have as explainable as interpretable AI decisions possible, no? And at the end, we all say that surgeon may maintain the final decision, but this is true when AI and clinician agree, no? But when they disagree, there can be a problem, no? If AI is right at the end, who is the liable for the decision made, no, when they don't agree, no. So in this kind, the ethical view of decision, it's quite tricky, because the clinician is always knows that if he followed the decision of AI, there will be no let's say liability if it's really not sure. So this part of our work, it's also very, very, very important in the project. No, I already mentioned the working with the training center, no, and this is not only the application part, no, but it starts with the dosage of ICG till holding how to hold the camera, and so preparing materials from video and documents it's quite a lot of work. No, going to our may work, as we are only technical partner in this project. No, at the beginning we have to develop the platform to support clinical trial communication, and to store all the data, videos, documents, and the data is pseudo-anonymized. It's not anonymized, because we have in the clinical trial you have to have the information backwards. No? So with information from the hospital and from our platform, you have to identify you can identify the patient. No, and I must say it was not easy to persuade hospital IT teams and ethical commissions, even if we possess ISO 9001 and 27001. We have to add the insurance and more other stuff and documentation. No? Some very important parts. No, when they upload the videos, we automatically detect the inflow point, and we can make a picture and image from that, and offer the clinician to annotate, and we have to add also the annotation tool to annotate these videos, while we have to make AI system learn from this annotation. No, maybe go on. The core of our technology is AI pipeline, where we have 3 steps. No, when we are tracking video for 5 minutes from RGB signal, no, and then implied in near. Then we plot the curves of intensity, and from this curve we do the feature extraction part. Now this is the second step, to understand the properties of the curves, and then we use them for the final classification part, now to understand if the tissue is cancerous or not, or benign. This is our testing program, no, where it's 8 times faster than in real time. For 5 minutes we have to track the tissue, which is already challenging while the patient is not still, and also the camera is moving. No, then we cover field with the grid, and we track these cells, every cell, and we try to curve smoothing and glare detection, and we have to understand every cell, then extract the feature. The features are time to peak, downslope, upslope, and then classify. And time is here very important, while 5 minutes for the clinicians is very, very, very long time. So we try to also to extrapolate and understand as soon as possible what type of tissue is under. This test program is CLASICCA Insight, is developed in Python and generates more than 45,000 data points, data files, images, videos with overlays, and so for each video this. And we have many videos and new arriving every week. So we constantly try to improve every step of this AI pipeline. So when we change something, we have to rerun all the algorithms on all videos. So we had to transfer code to HPC to run in parallel as much as possible, then have scheduled job, and then we automatically compare the results, because if we change something, we have to verify that the results are at least the same as previous one on the every video, no? So we really generate gigabytes of data and then comparing them every on every change of our pipeline. We are having development still, and then this Python AI pipeline is translated in Java, while this is a desktop offline program in operating room, no? And we have to test this library and then implement in the final application. One screen you can see here, no? We are lucky also because we have 3 clinical trials in this project, no? Already in. So while this is for someone who wants to produce a medical device, this is very challenging also to have clinical trials. So we have 3 clinical trials in each hospital, no? And in the first clinical trial, we gather only videos and annotation to make learn our algorithms, no? In the second clinical trial, which will start in a month or 2, we guide the biopsy, but so we already do all the classification, but we don't, let's say, the clinician cannot use the results we are presenting for their decisions, no? But only it has to take the biopsy where we when the program decides, no? And this is where we detect the main probability of cancerous tissue. And the third clinical trial will be about making a heat map and guiding also the incision of the tumor. While this is very important, no? Because if they cut too much, the quality of life of the patient is not so good, no? And if they don't cut all the cancer, we can presume what happened next, no? So we then aim to do the CE certification for our solution, which is quite a challenge, no? Although already the clinical investigation plan, investigator brochure, and to National Research Ethics Committee, and so it was quite challenging for the study too already, no? And but CE certification can be done after the clinical trial, and then we go to the medical device registration. Then, if we want to have the medical device, we have to look at the IP rights and the patents already in this area, and so it's quite quite important work to do before we get to exploitation. So in the medicine, times are always very long for us when we work in the, let's say, area more business-like. The time goes faster than in medicine. Every step is a challenge and takes time. And this is everything from my part. If there are some questions or okay, in chat.
So now you're invited to ask some questions for our speaker. So Gasper said, if I'm not mistaken, you said you use random forests for classification. Do you consider your model explainable enough?
This is, when preparing this, we use this slide. No, while we don't use anymore the random forest. This is the first thing. This is there while our project was based on a prototype made by UCD, University Clinical Center from Dublin, and IBM, and they did this and published this, let's say, pipeline, and so we use this let's say image picture in every presentation, while it's in many articles published. But this was only the first, let's say, from the prototype. We already changed and we are testing others. We are in this because we get many features from the curves, and with the classification, different approaches to classification, we now are trying to use as less as possible features, and features who are more at the first part of video to let's say shorten the time. So random forest is not the currently used. It's only in the picture, although we are talking about machine learning, so between explainable and interpretable, we are there. It's not black box, and we really try to make also to understand how to make the clinicians understand how the system works. And we had another thing, in every step of the AI pipeline, we decide the quality. Okay, so if the quality is not, let's say, not perfect, but over some threshold, at the end we say we don't give you the suggestion, while we are not sure that every step is working perfectly. And as for sorry, it's my timer. So we are working also in the unsupervised and also in other approaches, in parallel, but let's say we are now to have as much as possible the interpretable and explainable model. No, it's not final yet. Oh, data size, yeah. Data size, we have currently only 150 only for this kind of let's say cancer. It's okay. We have 150 videos, and we have to divide between learning and test data set, and the processing time, we aim to, this is the second problem, while we have 30 frames per second, and we test a lot, and we saw that 1 frame per second processing is enough, and now we are in real time with the processing. So if the video is 5 minutes, we are in real time giving the information also about the quality of the tracking and the curves between. So we give the clinician also this information during the intervention. So all the processing, all the saving, the making videos, images, and everything is real time on the, let's say, 8-core, 8 physical core laptop. Now.
Okay, thank you very much for explanation. So any other questions? Okay. So thank you very much, Samo. And meanwhile, I would like to introduce you the next speakers. So Dr. Mirianthi is a scientific coordinator at the Cyprus Institute with a background in applied mathematics and biomedical engineering. And Dr. Haralambous is an associate research scientist with a background in advanced machine learning and data-driven applications, and especially in omics and medical images data analysis. And in their presentation today, they will go through some of the success stories in the health sector, which will highlight the NCC Cyprus harness the power of HPC and advanced computational technologies for precise disease diagnosis and tailored treatment strategies. And if you are ready, then you're more than welcome to start.
I will start by presenting myself now. I'm Dr. QUSTom. You can call me Harry. Currently I'm an associate research scientist at the Cyprus Institute. I have some expertise in data analysis and machine learning, with more focus on medical health data analysis for classification, genomic analysis, and also medical imaging. Next slide, please. So before I go through the application we work with here at NCC Cyprus, I will talk about some problems we usually face. Is in the recent years we saw an explosion of data. There was a very significant increase in data collection, from simple things like electronic health records to also genomic information. We can see this in various fields, like, for example, with the establishment of National Biobank that collects this information. Also, various hospitals here in Cyprus collect and store specifically this kind of information, and also collaborate with each other to exchange this kind of information. I'm going to give some example later on. And also there is, I'm going to talk about the implication and the impact this data can have in healthcare, and also from giving different examples from in order to comprehend different kind of diseases, diagnose diagnose patients, and also to discover and decide appropriate treatments for specific patients through data. And the ultimate goal is to have personalized healthcare. Of course, these opportunities can have big challenges. Big opportunities always have big challenges. And also, we're going to discuss what specifically from our side these challenges are. Specifically for medical data, the first issue is the sheer volume of data generated. And this is a very big problem, because conventional processing methods are not suitable or adequate in even addressing the amount of data generated. And also because we have this recent trend that also institutes wants to share, integrate, and collaborate with them. The second is the complexity of the medical data that is generated, especially it's coming from multiple sources, multiple formats, and also in many cases they demand complex integration techniques in order to be harmonized and integrated. The last one is the last challenge is also the analysis of the needs of analysis to and new approaches in order to be able to extract valuable insights from these data sets. And also for these data sets, you have we are going to also mention some of the solutions that we can focus. Next slide, please. course, the first obvious one is to be able to utilize high performance computing. HPC in some cases is only the only way to be able to process and analyze sensitive medical data sets that can lead, of course, to quicker diagnosis, risk finding, and so on. In research development, as you can see everywhere now, you can apply deep learning and big data analysis in order to analyze this kind of data. This also help the field in order to identify significant pattern and also forecast in these patterns in medical data that will lead to better disease diagnosis, tailored treatment, of course, and predictive patient outcomes. One also recent addition is computational modeling. So, for example, there is also a very recent trend to digital twins through simulations that instead of working with with patients that have a specific disease or even lab animals, there is a trend to be able to simulate these physical models through digital twins in order to have a more faster development and treatment and analyzing the treatment effects. And also this enables improvement in treatment strategies, faster utilization of the knowledge, and also faster identification of novel therapeutic targets. So the next one, I'm going to talk about some applications. It's not the only ones, but it's some research application that we applied this, working through these problems and what solutions we went through HPC, machine learning, and so on. The first one is, for example, classification proteomic data. Proteomic data is something that we collect, it's not something recent, we collected information for around 100 years now through different samples, but through recent development in sequencing, we are able to digitize this information and analyze it. And of course, you have seen the recent like AlphaFold, AlphaMincent, that we have now potential models that they can give us very detailed and more accurate insight regarding proteomic data. So you have vast amount of data that is to be processed. And this is very crucial because in proteomics plays a very vital, vital key in order to understand our cellular process, disease mechanisms, and so on. So in order to understand this, every function in our body is performed most of the cases by a protein sequence. It also plays a very crucial key for biomarker discovery, monitor disease progression analysis, and also is often a target of therapeutic development. Some case studies that we have worked is also, for example, is very key in our days, like virus host interactions, especially after COVID. In this case, we focus on influenza virus in host interaction, which is a very important problem for the last few years with recent outbreaks for influenza. And another case study have worked with allergenicity prediction of because allergenicity is not a very straightforward problem, and the mechanisms that underline what causes allergenicity is still largely unknown. What we have applied is, in this case, supervised models, and then I can talk a little bit more, if you like, about CNS-based models and also unsupervised models in order to uncover hidden mechanisms that specifically for influenza and allergenicity that can, for example, give you better insights on how these different groups interact with each other. And the conclusion of these studies is that you can discover hidden subgroups, of, for example, of influenza or hidden mechanisms, especially not from human influenza, but from other species that have significant potential to be transmitted to humans and then can cause the next pandemic, of course. And also we develop models for classification of allergenic proteins that can have currently a very, very high accuracy, and then you can, of course, go into the huge volume of data of unknown proteins and then predict potential allergenics. Next slide, please. So next case study, it's a collaboration with the National Biobank. They are interested specifically for something called Alport syndrome. This is a very, nowadays it was thought before we have genetic testing, it was thought that to be a very rare disease, but nowadays with genetic testing, it seems that there is a not as rare as we thought, affecting us to 10% of the population, especially here in Cyprus. So, but this insight comes through. Also, I'll mention this is a very severe disease, especially if it's left untreated. So it's very keen to be diagnosed very early in order to start medication as soon as possible. But this, of course, is very recent addition. It is enabled by next generation sequencing, by the utilization of next generation sequencing, especially for Alport disease. What the problem is that, especially if you have worked before with natural sequencing, is the amount of is the volume of data that can be generated, especially if it's associated with physiological data. So, especially for this one, we have to enable HPC in order to analyze this genetic data in order to facilitate more precise disease classification. And also, there is also a problem with that because not every individual is affected the same. So we wanted to see, the Biobank wanted to see if it can use this kind of information to discover some hidden subgroup of the disease in order to expect to give more precise, personalized solution for each individual, especially if you are going to predict if they have mild or severe disease progression. So it was very important for them. Next slide, please. So, and this, the last for my part, before I pass the presentation to my colleague Miria, is the collaboration with the German Oncology Center. This is a private hospital that they specialize in prostate cancer. So they have a lot of patients that come with prostate cancer or suspected to have prostate cancer. So, and they do all the analysis specifically with MRI before they do a biopsy. So as you can see from MRI images, in order for a practitioner to be able to analyze thousands of individuals, it's very time consuming, and then it's very critical to have a very accurate classification and diagnosis, especially if the patient has cancer, because otherwise it will have significant consequences if they delay the treatment for the patient. So in this case, we use multiple models, but today I can talk about some supervised methods that we use convolutional neural networks in order to analyze this MRI data for classification and segmentation. And then this gives, because we have a lot of data from open and data, and also German Oncology Center has a lot of in-house data. We can analyze the data, and then currently we are at this stage for German Oncology to be able to have a very high classification and balanced classification accuracy that indicates if this any given slide of a patient has the potential to have a presence of cancer. So thank you for my part. Now I think Miria will continue her part of the presentation.
Thank you, Harry. Hi, everyone. My name is Miria Kachkaralambous, and I'm a scientific coordinator at the Cyprus Institute with a background in biomedical engineering and patient-specific computational modeling. Now, following from the work of Harris with prostate cancer images, let me briefly describe how we can use computational modeling in this case to improve the efficiency of prostate cancer treatments. So let's start with the motivation behind this work. Prostate cancer is one of the most common cancer types in men worldwide, presented with more than 1 million new cases each year. High-dose rate brachytherapy is gaining significant popularity as a treatment option due to its high survival rates and its overall minimal disruption in patient life. It involves the implantation of catheter needles into pre-planned locations in the patient's prostate, through which radioactive sources are delivered to the tumor site. Nevertheless, as the needle punctures and penetrates the prostate, it imposes substantial deformation on the tissue, which often leads to discrepancies between the pre-planned and actual position of the needle. Needle misplacement might impact the radiation that can reach the tumor site, and this in turn can cause a deterioration in treatment efficiency. So we took up this challenge through a data-driven in silico modeling approach, which simulates needle placement while accounting for the induced deformation of the prostate tissue. Notably, our models are personalized using comprehensive medical images acquired throughout the high-dose rate brachytherapy procedure. And the proposed in silico framework is anticipated to be useful for clinicians and medical physicists as a training platform through which they will learn to compensate for the effect of needle-induced deformation. And it could also be used for intraoperative guidance to predict the optimal location for needle insertion. Now let's have a look at the data that we have available for model personalization. Comprehensive data were acquired at the German Oncology Center, and this included MRI data acquired before the procedure. This image can give detailed information on the prostate anatomy and can thus be utilized for segmentations. We also had an ultrasound image prior to any needles, which is used together with the MR image for constructing the personalized computational domain. Then there was an ultrasound acquisition once 2 anchor needles were inserted. These anchor needles are used to keep the prostate in place. And finally, we have an ultrasound image acquisition once all needles have been inserted. This image can be used for identifying the needle location, which is used for personalizing needle insertion in the model. And it also gives the deformed domain, so it can be used for model evaluation and for giving directions for model improvement. Briefly, the process for creating the personalized models includes basic image processing steps, such as image registration, segmentation of organs of interest, and generation of the computational domain. In terms of model development, essential boundary conditions are imposed, and the needles are simulated to enter the prostate in a sequential manner. So first it will be the 2 anchor needles, and then the catheter needles are inserted. In the figure here, you can see some of our computational simulations overlaid over the medical images and the segmentation. So in contours are the actual simulation results, whereas the colored regions show the segmentation. We can see that there is a good agreement between data and model. And these initial results were very promising and show the potential of our approach to be used as a potential preoperative or training tool. Of course, further work is needed, but also in order to enable clinical transition, we would have to do validation studies. Okay, so now let's move on to another example of using computational modeling in healthcare, focusing on anti-angiogenic therapies for cancer treatment. So as the tumor grows, the existing vasculature becomes unable to support the increasing metabolic demands of the tumor. So vascular tumors cannot grow beyond a few cubic millimeters. However, angiogenesis, or the formation of new blood vessels, is able to satisfy the tumor's metabolic need as well as provide a means for its metastasis. As a result, angiogenesis marks a transition from the dormant phase to an aggressive and potentially fatal phase, constituting a significant therapeutic avenue. Now, because of this pivotal role of angiogenesis in cancer progression, anti-angiogenic therapies have actually received significant research interest, both as monotherapies or in combination with chemotherapy. Despite some very promising results in preclinical trials, however, benefits in actual patients have been underwhelming. So why is it that we don't see more important benefits by anti-angiogenic therapies? This could be partly due to our limited understanding of how they work, what are the main mechanisms of action, and how these interact. There are several known mechanisms of action. Most important are stopping the formation of new vessels, which delays tumor growth, the reduction in vascular density, which starves the cancer cells, improving the quality of the vascular network by decreasing pore size and surface area in a process known as vascular normalization. And also, anti-angiogenic drugs have been known to improve perfusion, which leads to improved drug delivery. Now, All of these factors are clearly affecting treatment efficiency. So there's a clear need for a better understanding of the effect of individual mechanisms of action, as well as their combined effect on tumor growth. These questions can be answered through in silico modeling, which creates the ideal framework for investigating the effect of individual mechanisms and their combined influence. This is a diagram of the model we used. It's a multi-scale, multi-physics model accounting for dynamic tumor growth, angiogenesis, vascular remodeling. It simulates tissue biomechanics and blood flow, as well as the delivery of the cytotoxic chemotherapeutic agent. This is the computational domain for the problem, which is solved using finite element method. We're assuming a healthy cube of tissue, and there is a region with cancerous cells in the middle. And the model also employs a discrete representation for the vascular network. Now, to simulate the different mechanisms, now let's focus on just one, reducing the vascular density. We did that by actually altering the discrete vasculature. So this is the tumor vasculature. This would be the vasculature once a low dose has been administered. This is what happens with a medium dose, and then we will have a high dose of such a drug. The tumor vasculature is actually very poor now. The animation here shows a control simulation of a tumor development on the left, and on the right, the simulation of a medium dose of an antiangiogenic drug. We can see that even a medium dose can cause the tumor to shrink substantially. The screenshots here show the final effect with different dosages of the antiangiogenic drug, with a high dose killing the tumor completely. Now, in a similar manner, we also looked into different mechanisms of action. And our simulations showed that when combined, antiangiogenic drugs and chemotherapy might be more beneficial than monotherapies. We also saw that metronomic chemotherapy has a significant potential even as a monotherapy. And as a conclusion, our in silico framework has shown promising results in deciphering the mechanism of action of antiangiogenic drugs. So as a conclusion, in this talk, we have briefly presented some of the work we have done on healthcare applications. Hopefully, we managed to highlight the huge potential of HPC, computational modeling, and high-performance data analytics for a better understanding of the progression of various diseases and for providing personalized treatment plans with enhanced efficiency. And this is only a small part of the activities we are doing at the National Competence Center of Cyprus as part of the EuroCC2 project. Main activities include liaising with local computational communities, identifying main needs in SMEs, academia, and the public sector, offering consultation services, and providing tailored training activities. If you want to find out more, you can visit our websites, and you can contact us at our email addresses. Thank you for your attention.
So thank you very much. And let's go ahead with the next presenter. So actually, what's the condition of your heart? So Miriam Gusha from Innovation DOL is an experienced IT expert and consultant, professor, innovator, manager, and entrepreneur with a broad knowledge and deep understanding of core business aspects and application of IT in a variety of projects, including cloud computing solutions, telemedicine, e-services, and IT service delivery. And today in his presentation, he will give us an insight into the solution their company is developing to prevent severe heart damage through long-term real-time heart monitoring. So go ahead, please.
Hello, do you hear me?
Perfectly.
Okay, I hope you see the presentation. It's about cardio HPC project, which was experimented within the EuroCC joint undertaking. And the project aims at improving the DL-based arrhythmia classification and also simulate real-time heart monitoring of thousands of patients. So as you mentioned, I'm owner and CEO of this company, which is a spin-off company of the university where I work as a professor. So let me start with dreams. Everybody dreams to live longer, and our technology can make it happen. Many are asking how. Well, cardiovascular diseases are the biggest killer in the world. More than 33% of all deaths are due to cardiovascular diseases. And we produce technology to prevent severe heart damage by long-term real-time heart monitoring. So let me explain about our technology. And the outline, what we are going to present is presented here. I will start with the business challenge and then present the solution and the HPC approach we have taken. So what were the objectives for our project? Objectives were to realize a real-time remote heart monitoring center for outpatients, so not for patients which are in hospitals. So patients can be at home, offices, even listening to this presentation. And the idea was to have a response less than 3 seconds, processing 10,000s of patients. And then also we like to demonstrate how can be done this with HPC platform. But what we are going to demonstrate today, what we are going to present, that we use the HPC environment to improve our existing deep learning solutions. So let me briefly explain what is on this figure. Here you see the wearable sensor, which is sending via Bluetooth data to the smartphone, tablet, or whatever it is, and this is sending to the cloud. And the doctors at the online monitoring centers are analyzing data. But since there is no possibility to analyze all 10,000s of patients simultaneously by one or let's say several doctors, our solution creates alerting system so they can analyze only the alerts. And now this is achievable. So our online software View ECG was awarded with CE mark as a medical device. We heard on the first presentation that Arctur has designed a new solution for AI solution, but they are still going to do it as a medical device. My advice is to do it as soon as possible because it takes 2 or 3 years to get the medical device CE mark. So the challenge was to train DL-based algorithms and to have fast and accurate results. So the main challenge we have done was to improve the machine learning and deep learning algorithms and to use extensive benchmark ECG databases, which were trained on thousands of GPU cores. Our initial models, which were trained before this project, were trained with small databases, and we got some performance indicators. But now we were able with this project, using this HPC technology to an environment to train with extensive number of ECG benchmark data sets. So what were the main outcomes? We reduced the costs and time to design a solution and conduct all these simulation experiments. We developed new features and increased the performance. We updated the business strategy and exploitation plan with new business opportunities, which allow us to create this online monitoring center for thousands of patients simultaneously. And what is mostly important, we reduce the cost for delivering a service simultaneously. So let me briefly discuss what we have done, what are the results. Here I present only 2 types of algorithms which were used within this project. The first one is ventricular beat classification. So normal beats are initiated by an atria and then followed by the ventricle. But ventricular beats do not follow this procedure, so they are coming only from ventricle, not from the atria part of the heart. And it is very difficult to distinguish between ventricular and atrial beats. Initially, our results were approximately 80%, and we increased this to 88% for sensitivity. For the positive predictive value, we increased from 80 to 90, and the overall F1 score was increased by 12.04%. When we executed the rhythm episode detection, practically AFib detection algorithm, we improved our sensitivity by 10%, the positive predictive value by 8.9%, and the overall F1 score 9.6%. Many will start to ask, okay, why didn't you reach the 100%? Or is it possible to do it? Maybe it is possible, but applying AI in medicine and trying to finding something which is specific and extraordinary, not normal case, is very difficult, because AI mostly can recognize what is normal and what is ordinary repeats every time. But if it is out of what is normal, then it can eliminate as a novice, or it can say this is out of the problem which was analyzed. So our experience shows that AI cannot reach 100%, but can significantly improve the performance which was initial. So what was the expected business impact and what we have reached? We have a ready-to-market service which can cope with increased workloads. And now we show that this is technologically and economically feasible. Then we reduced the error rate by 50%. So in the beginning, our performance was approximately 80%, which shows that the error rate was 20. And then we reached approximately 90% precision performance, which gives 10% of error rate. So the error rate was significantly reduced. And what was very interesting, because we got our CE mark in 2020, and every year we almost double the revenue. And last year, according to the income statements, our revenue was more than doubled, so 165% more than the previous year. So we have also 25% increase of efficiency and profit. And social impact, yes, we can now create new jobs, because doctors, salespersons, distributors can run such online monitoring centers. But what is most important, we improve the overall healthcare. And this project doesn't have any impact on the environment, because it is mainly based on software. So, but it reduces the transportation needs, so the patients can be monitored remotely, and they do not need to visit the doctor for appointment. And also, what is very interesting, their stay after the cardiac surgery or any other surgery, their stay at the hospital can be shortened. So the hospital discharging protocol can be changed with less days in hospitals, and having the patients still monitored 24/7 with this technology. So what were the lessons learned? We used a total of 5,000 node hours. By node, we mean 2 CPUs, and for NVIDIA Tesla M60 cards. We trained our new AI-based algorithms with heartbeat classification, arrhythmia, and our support from the FF4 Euro HPC was precious because we did the job we did the training in less than 1 year, something we would reach in tens of years if we didn't have this support. So thank you for listening. Our website is cardiohpcinnovation.com/MK. And I would be here to answer any question if you have.
So, dear guests, you are now invited to ask some questions. So we have the first one. So how many different heart conditions do you classify? Correct me if I'm wrong, but it appears that some conditions such as atrial fibrillation could be classified more straightforwardly. Considering the complexity and resource demands of deep learning, could you elaborate on why it's preferred over traditional methods for such classifications?
Okay, let me answer your question. So we also tested classical machine learning algorithms. We tested several of them, starting from random forest to many others. And practically XGBoost was the best had the best performance. Also, we started with deep learning methods. And currently, after this project was finished, we are also running something which is very interesting. It's another European project, which is creating ECG GPT language, meaning that we are creating tokens of ECG instead of letters and words in natural languages, and trying to find if we can use this technology for classification of arrhythmia. According to the number of arrhythmias detected, I can share with you our knowledge that you can detect two things. First, the bit type or bit class, and then the rhythm episode class. When you are detecting the bit type, you can detect normal, atrial, ventricular, fusion, or several other types of beats, but they are, according to standards, they are classified in these 4 essential bit types. So even blocks are treated as normal bit class. So the most problematic and with the very small performance is detection of ventricular beats. It is also found in all research articles, and according to our performance, what we get with this project, we are among the best algorithms. The problem is when most of the people are trying to use AI for evaluation of those algorithms, they are using training versus test models like 90-10 split or 80-20. And here they get very high performance, like 99%. But this is fake. Why this is fake? Because you're training and testing the same patient, so the same type of the bit. So what we used in our performances, what we presented, is to test with totally different patients, or using the Deschazal method of testing, where you have 22 patients for training and other 22 patients for testing. And these are the main results what we were presented here. When we are talking about rhythm episode detection, there are approximately 12 or more different rhythm episodes what we detect. Most of them are straightforward, like bigeminy, where you have pairs of atrial and normal beats, or triplets, or ventricular and normal beats. But some of the rhythm episodes, which are like atrial fibrillation or atrial flutter, are hard to detect. Why? In normal system, when the person is not laying in the bed, when the person is active, physically active, using a wearable ECG sensor, there is a lot of noise in the signal. And in these cases, you need something more, because the ECG signal has baseline wonder, has a lot of artifacts, and then these artifacts create a lot of problems to detect if it is atrial fibrillation or not. There are a lot of articles presented about detection of atrial fibrillation, and most of them are not presenting the real results, where the training is done on different patients for with the testing, where the testing or evaluation is done. And I don't like those results showing the straightforward detection of AFib with 99%, because these are trained and tested on the same patients, which is not good in medicine. I hope I answered this.
Okay. Thank you very much. So if there are any further questions, then you can leave it in the chat and we'll answer them afterwards if we have some time. But now I would like to go to the next presenter. So we have Dr. Panagiotis Papadimitroulas, which is co-founder and head of software department at BioNTech. And his expertise actually lies in the use of MC simulation and AI techniques for medical application. More precisely, his research and industrial activities are towards the evaluation and optimization of clinical diagnostic and therapeutic protocols, which the use of advanced computational techniques. And in today's presentation, he will present a case study on nuclear medicine dosimetry, explaining how to offer clinicians and possibility to assess the internal pediatric dosimetry and optimize nuclear medical imaging clinical protocols in terms of personalized prediction models. So if you're ready, we can start.
Good morning. Thank you very much, Tina. Can you see the screen and listen to me?
Perfectly.
Thank you. So good morning, everyone. My name is Panagiotis Papadimitroulas. As Tina already mentioned, I'm co-founder and head of the software department at BioNTech. And today I will try to give an industrial perspective of the use of HPC and our use, providing a case study on nuclear medicine dosimetry. Just a few words about my background. I'm a physicist and I did my master and PhD on medical physics, investigating the evaluation and optimization of diagnostic and therapeutic protocols in nuclear medicine using computational techniques. So in BioNTech, BioNTech is a company, a Greek SME, an innovative company in the field of biotechnology, and it focuses on molecular imaging, dosimetry, and biomedical engineering. And we have in the company three main departments, three main activities that we work on. The first one is that we design and construct benchtop imaging devices for screening applications, for screening radiopharmaceuticals for preclinical purposes. The second one is that we provide services in terms of preclinical imaging. And the third one that we are going to discuss today is that we provide computational solutions using Monte Carlo simulations and artificial intelligence techniques for investigating clinical and preclinical protocols. So in our department, we use a lot Monte Carlo simulations for both dosimetry and medical imaging applications, including PET, SPECT, and CT. Also, we develop AI algorithms for prediction models, providing applications for clinicians and decision support systems. And also we work a lot on image processing and image analysis using radiomics, segmentation, quantification, and reconstruction. And we use a lot 3D computational models, both for anthropomorphic models and animal models. And also we work with graphical user interfaces development, explainable artificial intelligence, and DNA simulations. So our first, let's say, experience in HPC comes from my PhD, where it was almost 13 years ago, where we granted an access in Mare Nostrum HPC Center under the HPC Europa 2 program. And there we had to implement very heavy Monte Carlo simulations for providing for simulating very realistic clinical situations. And afterwards in the company, we had a very short experience in our national HPC center in Greece, the ARIS HPC system, where there was a pilot call for applications involving industry. Unfortunately, since then, all the calls are for academia, but there are many calls around Europe that provides this access to industrial partners. Currently, since 2021, we are using a lot HPC, I could say, in daily routine in the company. And in 2021, we got a grant under the FF4 Euro HPC called a PEDIDOS project. It was called PEDIDOS. And we got access in the IOTA, a private HPC center in Croatia. After the project, we extended this access as we saw the benefits of the HPC. I will say more later. And lastly, since January last month, we got an access in the Euro HPC JU call under the development access in the Meluxina HPC Center. And there we are going to run the synthesized care project. I will say a few words afterwards. Just to give you the framework that we are working on personalized medicine. It is a medical model that aims to provide tailor-made prevention, diagnosis, and treatment of a disease for defined individuals or a group of individuals. The last few years, the term is precision medicine and not personalized medicine. And we have to deal a lot with big data, AI, and to develop digital twins in order to individualize our protocols. In this model, in the personalized medicine, we have to consider personal, anatomical, functional, demographic data of the patients and to combine them in order to reconsider our clinical protocols. The AI, you already know that it has become very important in medicine. There are several drawbacks in order to come in clinical routine, but they can help a lot in several fields, like around the world, there are many delayed diagnoses. The protocols nowadays are all fit one clinical protocols, but it should be changed. There are no individualized approaches. Also, between the different hospitals, there is no common expertise, or even between the clinicians. In some cases, in some countries, there is lack of personnel. Of course, AI can help in more effective management of the patients, more effective therapies, like having more effective follow-up processes. And of course, it can help a lot in order to reduce the no required clinical examinations, which is one of the scopes of personalized medicine. And lastly, nowadays there is a huge effort to develop decision support systems that would assist clinicians in order to provide a more accurate and more robust diagnosis or a therapy procedure. Taking the last point, I will go to present you the PEDIDOS project, which is actually the development of a DSS system, a decision support system. It was under the FF4 Euro HPC, and there were three partners in this project. BioNTech was leading this as an expert in the field. Also, we had the collaboration with another company as an end user. It is the I Know How company. It is an SME in the field of medical software, and they already have a product installed in several hospitals here in Greece. And also we had the GRNet, the Greek National Infrastructures for Research and Technology, as an HPC center. This project was implemented in the IOTA HPC center in Croatia, and it was under a subcontract. Here I would like to give you a very good statement from the call of FF4 Euro HPC that I think that it is very indicative for all SMEs and startups that work on innovative applications, and I would like to read it. It says that it targets highest quality experiments involving innovative agile SMEs and with work plans built around innovation targets arising from the use of advanced HPC services. And the key concept is to demonstrate SMEs how they can strongly benefit from the use of advanced HPC services and thereby take advantage of these innovative ICT solutions for business benefit. Before applying to this application as a company, we didn't have very good experience with HPC, and we didn't know our current needs and how we could use and take advantage of the HPC, but it really triggered me that we should give it a try. And the idea that we submitted and we would like to implement in the company is to develop a new product, a DSS, as I mentioned, that will focus on personalized pediatric dosimetry prediction prior to the examination. It means that it will give the clinician, the medical physicist or the oncology information, a prediction of the absorbed dose that the patient is going to receive based on its individual characteristics. This methodology was previously developed in a Marie Curie RISE project. So what is the problem around this? In nuclear medicine procedures, the radiopharmaceuticals, they have radioactivity, and this radioactivity has ionizing radiation that deposits energy in human body, and this energy is the absorbed dose in the organ that it can lead to cancer. And also, pediatric patients are much higher radiosensitive than adults. In clinical practice, it is difficult, it is impossible to measure the absorbed dose in each organ of the body, and only assumptions and rough estimations are applied in clinical routine. And this is the reason that the protocols are very generative, and for a child, let's say 5 years old, and a child 7 years old, they will apply the same protocol. So dosimetry nowadays is done after the radiopharmaceutical injection, which is quite late because the patient has already received the absorbed dose, and we don't have this information. So in order to solve this problem, we used, and this is the reason that we needed the HPC, we used a population of 30 pediatric computational models in a different, covering a range of ages from 2 years old to 15 years old. So these models had different anatomical characteristics, both boys and girls. And for our proof of concept development, we used the 5 most common radiopharmaceuticals with 4 different time points for each one. And it concluded to 500 different simulations. but they are quite heavy in terms of computational time because we needed to have very, very low statistical uncertainty. It means that we needed to have many, many particles simulated. And also, after creating this simulated database, we performed some trainings in order to have the prediction AI model. So in this case, these two figures, the activity map and the attenuation map, is the input in the simulation, what we provided in the HPC as input. And the output is a 3D matrix with a dose map, the observed doses in the whole body. And from there, we can measure in each organ the observed dose. So in the end of the project, we developed a novel software product that offers the clinicians the possibility to assess the internal dosimetry and optimize their nuclear medicine imaging protocols in terms of personalization using anatomical characteristics of the patient. Here is a preview of the graphical user interface. So the clinicians here can select several features like the age, the gender, the height, the weight, and also some other features that can arise from a CT image of the patient or an MRI image of the patient. And then they select the appropriate radiopharmaceutical and the activity that they want to inject according to their protocol. So the outcome of this tool is a report with the absorbed doses per organ for this specific patient. And here you will see a demonstration. I will pass it a little bit fast just to explain you that this Evorad system is the software product that I know how the other company of the project has already installed in the hospitals, and it is a medical image processing tool. And here we combined the pedidose feature, this button. So why we did this combination? Because the clinicians already have this tool, and they can do specific measurements. And clicking afterwards the pedidose, it opens directly the tool that we developed. The clinicians put the parameters here, select the appropriate radiopharmaceutical, and after the calculations, it takes less than a minute, the prediction, the algorithm in order to do the prediction. We have the output here, the estimated absorbed dose per organ, and it can also be exported as a PDF for the clinicians. This was the first tool that we developed using HPC in the company, and now I will be very short just to give you an idea what is the next tool that we are working on using HPC. Here, the idea is to develop a tool for auto creation of an anatomical model for each patient that goes to a hospital and undergoes a CT or an MRI examination. It means that a patient that undergoes an examination, then we could have directly an anatomical model of this specific patient. In this case, we are going to handle very big data, auto-segmentation tools. We are already in contact with 2 hospitals that will provide us thousands of clinical MRI and CT scans. And the idea is to create, using HPC resources, synthetic data. So we have described the collection of more than 2,000 clinical examinations. The processes for the organ segmentation will be done in the Meluxina HPC. And after extracting all the organs of each CT, then we are going to create an anatomical fandom. So we will have a set for this specific data set, a set of images, 1, is the clinical image, and the other one is the anatomical map of the patient. And after evaluating these anatomical models, the creation of the models, then we will train an AI model in order to directly export from a clinical CT scan the anatomical map of the patient. And the idea is to have it in all hospitals, and this anatomical map could be stored in the medical record of the patient for further purposes, like investigating a treatment plan or like these applications like this. So here, having the idea of the two, let's say, cases that we have in the company focused with the use of HPC, I would like to share with you some thoughts about how we were benefited from using HPC. First of all, after 2021, with the PEDIDOS project, we developed an autonomous software department in the company, and we had a very good collaboration with the other SME in the software in the medical software market. Finally, we managed to exploit prior knowledge and experience with computational tools because previously we didn't have the resources to provide such models. They need very high computational time. And it gave us the opportunity to develop novel products and very focused for specific applications in clinical routine towards personalization. Also, it provided the combination of AI with HPC provided the ability to have innovative solutions. And also, we were much more competitive in the market having this tool. And also, another point that I would like to mention is the importance of having the staff trained on HPC procedures in order to implement such developments. So more precisely, of course, it was mentioned also earlier with the other presentations that there is a very good gain speed in terms of execution time. And also we had in BioNTech the ability to extend the HPC not only for Monte Carlo simulations for the project that we were running, but we took this advantage and investigated how we can use the HPC in order to provide software features for our hardware departments, for our hardware devices, the systems that we are developing. And it provided us very robust results, having very low statistical uncertainty. So the training of the personnel, as I already mentioned, made it is a very competitive knowledge for research purposes and grants. It opened us the path to submit other proposals with the experience of HPC. And we already use it for training models, for deep learning, mainly for imaging datasets. And yeah, we already seek to see how else we can use the HPC in daily routine. There was a thought for many years in the company if we should build in-house a cluster. And now with the HPC, I think that it was a silly idea because with the HPC, we can do very demanding and complicated calculations quite fast. So I would like to share with you that HPC could be considered in a company for business purposes as a tool for daily practice, as a tool for the developers of the company, like we use the cloud services or the cert files or other tools. There are many sectors and fields that could benefit from HPC, at least in the healthcare domain, like clinical data processing, patients management, personalized medicine, simulations, and AI. But there are few drawbacks, like how we can access HPC, because if the resources are quite expensive, and we need to find to at least get grants or funds for having access. And it is very important to have an expert, at least in the beginning, for applying these procedures on HPC resources. And also, I would like to mention that from my experience, many SMEs and startups are not yet aware of the benefits of HPC and how they can enhance the quality of the results and their products, and how they can implement HPC in their daily workflow. So I believe that activities like the event today or other dissemination and training activities are very important in order to make it clear that industry can benefit from such infrastructures. But it is also very, very important for the industrial side to identify its needs. At least for us, it was, and I believe that it still is, very difficult to define what are the needs for a specific project, how this very specific process will run on an HPC and will be parallelized, and how many resources we should ask. So it is very critical to identify whether and how we need the HPC. So concluding, here are some limitations and challenges that we face as an SME in the healthcare domain. There are, of course, ethical issues, very well known. The acceptability of the developments of AI in clinical practice is very difficult due to trustworthiness and robustness. Explainability is very important. Data harmonization and standardization of data. Also, it is very difficult to change already applied clinical protocols. But in all these, resources like HPC can help, can aid in order to make them happen. Some other challenges are the training of the personnel in new techniques, in new infrastructures. The regulations are always required. And also, it is very important to involve several stakeholders around the new developments, the new technologies, like researchers, clinicians, patients, legislators, industrial partners, and regulators. So I will conclude with this image that we are now in the era of AI, and in medicine it is real, it happens. But I strongly believe that HPC can help in order to bring AI in a clinical routine. So I would like to thank you, and please to answer any question if you have.
Yeah, thank you very much. So this is actually a really valuable presentation, also in the scope of the businesses. So I would like also to mention here that new founding program of the Fortissimo project is upcoming in the next months. So all, especially SMEs, please keep your eyes on the information. So there will be quite a lot of money available for the next studies in scope as presented by Mr. Panagiotis. So we have also one of the questions in our chat. So it says, do you use in-house built Monte Carlo software, or do you utilize open source software like GATE for dose estimation? What level of accuracy do you aim for in your dose estimations, and how is it predicted dose verified?
Well, exactly. Very good question. Thank you. We open an open source software. It is the GATE open source Monte Carlo simulation toolkit. BioNTech is an official member of the Open GATE collaboration, so we participate in this collaboration. And the accuracy of the predicted doses, we achieved a statistical uncertainty lower than 2%, which is very good for nuclear medical purposes. You can imagine that the estimations for nuclear medicine dosimetry is around 5 or even 10 percentage off sometimes. So and how is the predicted dose verified? Okay, you mean the accuracy of the prediction models, I suppose. It is done with specific metrics. We use several metrics like the mean, the RMSE, there is a publication on these results with the PEDIDOS results describing exactly all the metrics and the accuracy of the algorithms. And also just to mention that we used combination of metrics in order to standardize the prediction of the results. And of course, as I mentioned a little bit in the presentation, this was a proof of concept. We wanted to see if this tool could really work, and we used a population of 30 patients and only for 5 radiopharmaceuticals. These metrics can be, the robustness of the models can be for sure increased if we use, let's say, a population of 10,000 computational models.
Okay. So thank you very much. If there are any questions left, you can leave it in the chat, and I will make sure that we are coming back to the presenters and give you some answers later. So now we are actually coming to the end of this event, and the last presentation will be done by 2 speakers. So I would like to welcome Ana Maria Rodriguez, a head of women imaging in Breast Cancer Center and Vall d'Hebron Hospital, where she's working as main researcher for molecular medical imaging, and Jan Harey, who is the head of research and development at Arctur, and he has a strong background in development, system engineering, code, and process optimization. And together they are presenting the QUSTom project, which is revolutionizing breast cancer diagnosis and screening with supercomputer-based radiation-free imaging. So you can start with your presentation.
Okay, well, I'm the head of department of women imaging in Hospital Vall d'Hebron, and I'm gonna explain in 10 minutes the why and the how the QUSTom project help us in the talking about the medical point of view. So Hospital Vall d'Hebron is the second biggest hospital in Spain, is the biggest in Catalonia, and we are a breast cancer center. We belong to the European Organizations of Breast Cancer Institute, and we attend more or less about between 600 and 700 cancer cases per year. So we are a multidisciplinary breast cancer unit with all the technology, and we are working closely with the Vall d'Hebron Institute of Research. That is an independent institute of research, as his name says, and We work also with the Valle Institute of Oncology. So we belong to the Barcelona University, and we have a lot of projects ongoing, but I'm very happy to share the QUSTom project with you. So why we try to find a new diagnostic tool? Well, you can see here two graphics. One is the number of images that a radiologist used to see and here you see how the amount of images per exploration, you have CT and MRI, is increasing. This is just an example from 1999 to 2010, and you can see how the number of images that we have to see per test and in general is completely out of our control. And this, of course, has an impact in our daily practice. And you can see from review from 2015, the radiology was one of the more the specialty that present more percentage of burnout physicians by a specialty, and of course the less happy in our work. So the radiologists need help. We need help, and we can understand that AI is solving problems. That's why we are prepared to change our daily practice. We are not ready to be replaced, of course, but we need help. And during the diagnostic process, we can have some help from the AI in the different steps from the diagnostic process. And you can see here, we organize our daily work, for example, in protocoling or reviewing prior images. But the focus nowadays are in detection of anomalies, segmentation, measurement, classification of findings, of course. But we are also have we need some help in reporting, of course. And what about breast cancer? Well, breast cancer is the most frequent cancer in women. Here we have an image from our screening program. You know, in Europe, we have institutional national screening programs. Our is one of the biggest. We have more or less 30,000 lectures per year. So from this diagram shows from 1,000 of women, we are going to recall more or less 50 of them, and we will find cancer in 4 of them, and 1 of them will be missed. 1 cancer will be missed. So this scenario is why we need to improve our capacity to the interpretation of screening mammogram. And this is just an example of the volume of images that we have to analyze to find 4 cancers plus, and we miss 1 of them. That's why we need help. There's a lot of images because the population is big, and we are doing the screening test from the population between 50 and 70, but the European guidelines recommended now from 45 to 75. Okay, so it's a lot of work for the radiologists. And you know, the breast radiologists are, we are few. There's not enough radiologists to be able to read this amount of images. And the second problem is the density, the breast density. And here you can see the classification of the American College of Radiology of the breast density in a mammogram. So you can see from the fatty breast to the very dense breast, and we have the cluster of fibroglandular tissue in the density B, and we have heterogeneously dense breast in the density C. And we are trying to improve our ability of detect cancers in all of these types of breast. Of course, it will be harder to find something here than here because of the density of the fibroglandular tissue. And we are trying to find a way to be more specific and sensible in these matters. And this is a case from our hospital. This is heterogeneously dense breast. It's a C classification of density. And you can see how we can pick this no tiny lesion. It could be maybe almost 2 centimeters of nodule. And we just are able to see it because a tiny microcalcification here, but we are not able to see a mass. And we are able to see it with the contrast. And hence, we give to the patient iodine contrast, and we do contrast enhanced mammography. And that's the way to improve the capability of the basic or 2D or 3D tomo mammography to improve to and be able to find lesion in this dense breast. And this is the MLO projection. You can confirm the and mass enhancement here and some fibroglandular benign enhancement in the contralateral breast. And here you have the late acquisition in the contrast enhanced mammography, and you have the image in the ultrasound. So here we have two techniques. We have the mammogram, improve it with the administration of contrast, and we have the ultrasound, but none of them are enough to see all types of cancers in all types of breast because of the density and the positive predictive value of the test. And the correlation with the MRI. So we have the third diagnostic technique, who is combine the contrast enhanced with the anatomical definition of the MRI. And we can see the same nodule is a lot of intraductal carcinoma. You can see here as non-mass enhancement associated with the infiltrative tumor. And there's another problem. The problem is the patient opinion, of course, and the perception of the general population about the mammography. And the mammography is a test who is uncomfortable for the woman. Nobody can say that compression of 75 newtons are something that is not a matter to improve. We need to find a diagnostic tool for screening in a general population who could depict the cancer, but who can also be less aggressive with the population. And this is a publication from my previous working group in Hospital del Mar, and we find that the women's preferred experience in the mammography using a self-compression device because the women are able of controlling the pressure, and the mammogram is less aggressive when the woman has a feeling of the compression is controlled by herself. And that's why QUSTom appears, because we need to find a new device without radiation. It means using ultrasound technique, because that's what we are using in our daily practice, but the mammogram we see is not enough. The ultrasound by itself is either enough. That's why we need to create a tool without radiation, with all the benefits from the ultrasound, but with the sensitivity and specificity and positive predictive value of the test with radiation as a mammography. Because as we know, the mammography is the only test that is able to reduce the mortality for breast cancer. But we need to continue improving, and it will be with AI, and as well my colleague will continue the explanation. So in Resume, we are trying to develop a new diagnostic tool without compression and without radiation. And that's my presentation. Thank you, Tina.
Thank you, Anna.
Thank you, Anna Maria. Thank you. Thank you, Anna Maria. I will now present the technical aspect of the QUSTom project and its usages and the HPC uses in it. Yeah, I'm sure you've heard of Arthur today, so I'm skipping this slide. So the QUSTom project was promoted by the European Innovation Council, which supports the research teams to research and develop new breakthrough technologies. In our cases, this was ultrasound imaging of the breast. This Pathfinder projects are usually high risk and high gain projects, so you can go really high or you can go really low. But they delve with cutting edge science. Why am I telling you this? Because for the QUSTom project, as Anna Maria said, we had to develop new ways, more comfortable ways for the patient to be recorded for the diagnostics of breast cancer. And for that, we needed to develop a lot of things from scratch. This included the hardware, the software, and the theoretical knowledge itself, the mathematical knowledge behind this. This effectively split the project into 3 areas. It was the exact 3 areas that I mentioned now. So we needed to develop ways to capture this data, to process it, and then to analyze or to measure the accuracy of the produced images of the data. The original idea of the QUSTom project comes from geology, actually. It's the usage of full waveform inversion, which deals with measurements of seismic activity in the Earth. You can see down here in the image, these are the seismic waves of a 2D image of seismic waves in one part of the Earth. And this waves passing through Earth can be very similar to waves passing through any medium. It can be even waves passing through human tissue or human breasts. And this is how you can perform full waveform inversions on human breast images or the ultrasound images of human breasts. So the first part was, as I said, the hardware. It was the development and the development of sensors to acquire the data of the ultrasound imaging. So this is something that our partners at KIT did. They developed new transducers or sensors which were able to emit and record ultrasound waves. And all this had to be then packaged into a device, a USCT device, which you can see on a sketch in the bottom. And this device features an aperture, which is in this picture filled with water, a medium that is the most easiest to work with ultrasound. And this aperture is filled with the sensors or the transducers that the KIT developed. If I can continue here, this is the aperture, the close-up of the aperture, the animation of it. And we can see that this aperture has many transducers. The transducers are these little things placed all around the aperture. And these transducers allow us to surround the object or a breast or a cancer lesion with unfocused ultrasound waves. Unfocused just means that they are spread all over the aperture, they're not directional. These waves are then recorded by the receivers, so by the transducers themselves. But the wave is triggered by an emitter. This is also a transducer, but they're also only triggered by one emitter at a time. So the receiver let's focus on one receiver now. The receiver captures two waves, as we can see, the original wave coming from the source, and the second wave, which is the bouncing wave that bounces off the object. This wave is then stored in a pressure over time signature format. So we have many receivers capturing all the pressure data coming from one emitter. But then this process is repeated continuously, so that we get, in a sense that each of the transducers emits in one part of the time in the diagnostic of the patient. So we get the representation, a proper representation of 3D image of the object. But when I say a proper representation of a 3D image, I mean this is just raw data of the pressure applied at one point in time. There is no actual image recorded at this point. It's just the data recorded by these transducers. This process with the aperture, this USCT device was developed, as Anna Maria said, to ease the actual procedure on the patient, to reduce the stress on the patient. The breasts are set in this aperture, and the aperture then records this. There is no squeezing of the breast or any violent action here. If we check, or if we see the USCT device closely, this is the actual elements that are composing it. So on the top left here, we have the transducers. This is the raw version of the transducer, and this is the assembled version of the transducer, which goes into the aperture. On the right here, we have the aperture with the rotation and lift mechanism. This allows us to position the aperture so that we have more accurate or better images, resulting images at the end of the patient. On the center here, we can see the aperture with assembled transducers, with all the wiring needed for the transducers. And on the left here, we can see the aperture built into the USCT device, which is basically a table with this aperture and a processing unit under it, as you can see. Okay, then after this data is recorded by the device, we need to use this data as an input to the algorithm. So we need to produce 3D images of the breasts so the medical staff can analyze it at the end. And for this, we need to input all this raw data of the pressure, of the recorded pressure for each transducer into the algorithm. There are two major problems with the algorithm, and the first one is the actual computational complexity is very high for this full waveform inversion problem. This is because you need to calculate the effect that all of the pressure waves combined had on one point in time, or one pixel in time. And meaning that if we want high resolution images for the medical staff to easily spot some cancer lesions, we also need to compute these pressure waves across many different or across large number of pixels. And that means that the computational complexity of the algorithm grows with the resolution of the image and its frequency. The second part of the problem here is the amount of the input data. So the data produced by the KIT device, the USCT, is measured, it ranges in hundreds of gigabytes, and in some cases it can also range in terabyte worth of data. That means that there's a lot of storage required for the actual algorithm. This is where the HPC comes in place. this greatly eases working, developing, and the execution of the algorithm which produces these 3D models. This is, of course, done by utilizing a high number of CPU cores, which allows us for greater parallelization of the software. This was also our part in the project, to parallelize the actual algorithm and speed it up. But this can only reduce the time complexity part of the algorithm, but not the actual computational complexity. The computational complexity stays the same because we have so and so big images, and we need to compute each pixel for it. Additionally, we have a problem of storage and working memory. So when the algorithm is working, we need to feed it constantly with this raw pressure data that was acquired by the device. And this data is, as I mentioned, is huge. So the working memory of the algorithm part has to be huge. And apart from that, we also need some vast amounts of storages just to run the algorithm on one case for one patient. That means that during the algorithm's execution, we produce a large amount of I/O operations. This is to read and write data to and from the storage. The actual end result, the image, the 3D model, is not that big, but the intermediate steps that we need to take to produce that model is it takes a lot of storage, because you need to store all of these pressure waves for each pixel. At the end, the last part is the actual image reconstruction. So the end result of the algorithm is to provide some 3D model at the end. So the medical staff can take a look at it and diagnose the patient properly. But apart from that, these images can help us to use as a feedback to improve the algorithm and the USCT device itself. This is during the project, of course. When the project is finished, everything needs to be done. But during the project, during the development, we can still use that feedback to improve the accuracy of the data and algorithm itself. So this reconstructed 3D models can have many applications. Why is that? Because when you have a 3D model, I'm sure everyone is aware of this, but when you have a 3D model, you can represent any part of it as a 2D representation, which allows us to view the object from many different points of views of the object. So we can apply it for different usages. We here have some applications of the actual model at the end, the end result of the model. We can see that we can measure density across the breast. We can see that we can measure, we can capture cancer regions across it. Here on the bottom part, you can also see there is still an outprint of the actual transducers in the aperture itself, this round shape. So yeah, this can be then applied to the real life use cases using the HPC. But without the HPC, the time complexity of the algorithm itself would be too much. It would take a lot of time. Usually now it takes about an hour and a half to produce such an image of the recorded breast. This is done on an HPC with the already parallelized algorithm and optimized algorithm. But this can be, of course, always improved in the future. But for now, this is what we have. This greatly improves the initial test that we were making with this software, which took a day or two to provide the end result. But we still have some work to do to provide some good results at the end. This was it from my side. Thank you to Anna Maria for presenting the medical part. And if someone has any questions, I'm available.
Thank you, Jan. Thank you, Anna. So we have a few questions in the chat box. So I would start with the first one. So what is the anticipated spatial resolution? And do you expect to detect microcalcifications which are a risk factor for breast cancer?
Well,
So, yeah.
Please
Okay.
continue, Jan.
No, Anna Maria, you can.
Yeah, the idea is the spatial resolution will be, of course, better than mammography. In mammography, we are able to see microcalcification. That means 1 to 3 microns. That's this kind of resolution we need to work out more because they are really easy to see with X-ray, but they are not easy to see with ultrasound. Actually, we just depict microcalcification in ultrasound when we know that they were in the previous mammogram, and that's a challenge. And of course, it's a risk factor for breast cancer, and is the most frequent radiology feature that is associated with intraductal carcinoma. That's why we are not so worried, because in many scenarios, clinical scenarios, the microcalcification something that is more a marker for risk of breast cancer. But in many cases, we don't need to biopsy or treat it because there's just proliferative diseases. But yeah, that's something that we are working in. And I don't know if Jan want to add some other comment.
I can also add, it's not just this fact, which you described really good, Anna Maria, but it's also the fact that this method tries to ease the procedure for the patient, right? And it tries to minimize the risk done by the capturing agents. I can also answer the second question from Gaspar. With what is the anticipated reconstruction time in CPU hours? Yeah, as I mentioned at the beginning, this was a couple of days. The reconstruction of one measurement of one procedure of the patient, but this is also, and now it's about an hour and a half. But this is also, as I said, it depends on the resolution and the frequency of the recordings done. So we can adjust these parameters a bit to get faster or slower times of the computation of the algorithm. I hope this answers your question.
Okay. So at that point, we came to an end of this event. So I would really like to thank you to all speakers and all you guests because you make this event really precious. And this was actually the goal of the event. So exchanging good practices, good cases, and somehow connecting this research and business area, which is really important to bring new outcomes, to bring innovation and make our, let's say, medical sector and health, of course, of people brighter in the near future. So I would like to thank in the name of the NCC SLING Slovenia. We are upcoming soon with the new events like this, where we will present new use cases from some other industrial sectors. You can reach us out in our website or social media, which is provided in the chat link. And so hopefully we will welcome you really soon in the next event. Thank you and have a nice afternoon.